Hello, everyone. I am Ma Zhenglu. I am from Sichuan Vocational College of Chemical Technology. The stress-strain curve of polymers is an essential tool for understanding and predicting how polymer materials behave in practical applications. By analyzing these curves, we can better select suitable materials for specific applications, thereby improving product quality and reliability. Today, we will study the stress-strain curve of polymers. First, let's study the stress-strain curve of amorphous polymers. The stress-strain curve of amorphous polymers is shown here. The stress-strain curve of amorphous polymers reflects the relationship between strain and stress when the material is subjected to tensile force. This curve typically includes the following key points. Yield point Y in the figure. Before this point, the material undergoes elastic deformation. That is, there is a linear relationship between stress and strain. This follows Hooke's law. After the yield point, the material enters the stage of plastic deformation. In this stage, strain continues to increase, while stress remains constant or decreases. Yield strength, the stress value at the yield point. It represents the material's resistance to plastic deformation. Fracture point, the material ultimately fractures at a certain stress level. The fracture point represents the maximum stress the material can withstand. The stress value at this point is called the fracture strength. The strain value at this point is called the elongation at break. Strain hardening, in some cases, after the yield point as strain increases, stress also increases. This is known as strain hardening. Strain softening, in some cases, after the yield point as strain increases, stress actually decreases. This is known as strain softening. However, the curve typically also exhibits the following stages. Linear elastic region. In this region, stress is proportional to strain. That is, it follows Hooke's law. The deformation of the material is reversible at this stage. After removal of the stress, the material can return to its original shape. Plastic flow region. After exceeding the yield point, the material enters the plastic region. The stress increases, but the rate of strain increase slows down. In this stage, the deformation of the material is no longer fully reversible. Necking effect. During the stretching process, some polymers exhibit localized thinning in a specific area. This is called the necking effect, which is usually caused by the orientation and slippage of molecular chains. These key points and the regions between them help us understand the mechanical properties of amorphous polymers. For example, their elasticity, plasticity, and toughness. By analyzing this data, we can predict the performance of materials in practical applications, and accordingly select the most suitable materials. According to the shape of the mechanical property curve, the stress-strain curves of polymers can be roughly classified into 6 types. Type 1, hard and brittle materials. They possess high modulus and high tensile strength. They have no yield point. The elongation at break is generally less than 2%. They undergo brittle fracture under stress. They can be used for rigid products, but they are not suitable for impact loading. They can be used for materials bearing static pressure. Typical polymer materials include PS, PMMA, phenolic resins, etc. Type 2, hard and strong materials. They possess a high modulus and high tensile strength. The elongation at break is about 5%. They exhibit little to no yield elongation. An example is rigid PVC. Type 3, strong and tough materials. They possess high modulus and high tensile strength. They have a relatively large elongation at break. During stretching, necking occurs, and the material failure is predominantly ductile. The stressed area turns white. Examples include polycarbonate, nylon 66, polyamide, and polyoxymethylene. The aforementioned three types of materials, due to their high strength, are generally used as engineering plastics. Type 4, soft and tough materials. They have low modulus and low yield strength. They have high elongation at break. Their fracture strength is also quite high. They are used in applications requiring large deformations. Examples include vulcanized rubber, polyethylene, plasticized PVC, and polytetrafluoroethylene (PTFE). Type 5, soft and weak materials. They have low modulus and low tensile strength. However, they still have moderate elongation at break. An example is unvulcanized natural rubber. These characteristics need to be utilized during processing. They are blown into the desired shape and then vulcanized. It then becomes a Type 4 material. Type 6, weak and brittle materials. These are generally oligomers and cannot be used as materials. Generally, the strength of a material can be judged by its fracture strength. Hardness and softness can be judged by the magnitude of the elastic modulus. The elastic modulus reflects the stress required per unit elastic elongation. It indicates the rigidity of the material. Its unit is megapascals. For general polymers, the range of elastic modulus is rubber 0.1 to 1.0 megapascals. Plastics is 10 to 10 to the third megapascals. The toughness and brittleness of a material can be judged by the area under the curve. So-called brittle fracture refers to the material fracturing before reaching the yield strength during stretching. The elongation at break is generally small. Consequently, the area under the curve is small, and the fracture surface is relatively flat or has a conchoidal appearance. Therefore, the magnitude of toughness can be measured by the area under the curve. It represents the maximum energy absorbed by the material before fracture. In practical applications, due to the viscoelasticity of polymers, their stress-strain behavior is significantly dependent on external conditions such as temperature, strain rate, and hydrostatic pressure during stretching. Next, we will study the stress-strain curve of crystalline polymers. The stress-strain curve of unoriented crystalline polymers has a more distinct transition compared to the tensile curve of amorphous polymers, as shown in the figure. The entire curve has two transition points. It is divided into three segments. In the initial segment of the curve, stress increases with strain, and the specimen elongates uniformly. After reaching the yield point, the specimen suddenly becomes thinner at one or several locations. This is called necking. This marks the beginning of the second stage of stretching, the neck stage. The characteristic of this stage is continuous increase in elongation, while the stress remains almost constant or increases only slightly. This continues until the entire specimen becomes thinner. The third stage involves the uniform stretching of the neck polymer specimen. Stress increases with increasing strain. This continues until fracture point B. Crystalline polymers generally consist of both crystalline and amorphous regions. The formation of their neck involves deformation in both the crystalline and amorphous regions. Crystalline polymers can form necks within the temperature range from Tg to Tm. After removal of the tensile force, they can partially recover to their unstretched state simply by heating to a temperature close to the glass transition temperature. Finally, please pay attention to two important points. First, the tensile behavior of real polymer materials is very complex. They may not possess the typical characteristics described above, or they may be combinations of several types. For example, some materials, when stretched, exhibit obvious yielding and necking, while others do not. Some materials have a fracture strength higher than the yield strength. In other cases, the yield strength exceeds the fracture strength. Second, the tensile process of materials is also significantly influenced by environmental conditions and testing conditions. For example, Rigid PVC products of the hard and strong type, when stretched at very slow rates, can also exhibit an elongation at break greater than 100%, demonstrating characteristics of being hard and tough. In this lesson, we primarily discussed the stress-strain curves of materials. We studied the types of stress-strain curves. That concludes today's lesson. Thank you for listening. See you in the next class.